Well, okay, so wow, we move to the next topic, linear programming. Oh, by the way, you have any questions regarding last time? Yes, we spent 1 week, right, on the classical optimization. Okay, and well, if you check my video and also what's it, the file I sent after the class, I add well example. Okay, application of the classical technique, including Lagrange method and KKT, Courage-Kuhn Tucker method, right? Okay, and you see, well, how well the application of those theory, how we can, yeah, apply those theory we learn for the well optimization problem. I mean, to solve to find the minimum point subject to constraint, yeah, equality constraint and also including inequality constraint. Of course, for inequality constraint, it's more complicated, right? And once we use KKT to identify those critical point, it can be minimum or maximum. Then you can use the concept of convexity, right? To to check whether those points are minimum or maximum. Okay. Yeah, the concept of convexity. We need why do we need that electric fan? Air conditions not working? Oh, it's okay. Yeah, but the temperature is okay. Yeah. Okay, so we move to linear programming. For linear programming, it's an optimization method applicable for the solution problems in which the objective function and the constraints appear as linear function of the decision variable. Also, the constraint equations, also inequalities, also, well, they are all linear functions, okay? You need linear objective function, also all the constraints, no matter their equality or inequality, as long as they are linear function, linear programming can be applied, okay? And the important things about linear programming is, of course, it's easy. However, the minimum point or even maximum point cannot be determined by using classical technique, right? Classical optimization technique, because the necessary condition, you remember necessary condition for the optimum point we learned last week. At the optimum point, the derivative must be in all direction must be 0, right? However, in case of linear programming, if you look at the objective function, we cannot have the point which with what's it 0 tangent, right? We cannot have a point with 0 derivative, right? Always while look at the linear function. For example, we have linear function. This wow, you can extend the line of this pen, okay, above and below. But once you take derivative of the objective function, it's a linear function, of course. So the derivative becomes a constant instead of 0, right? So you see that we cannot use classical optimization technique to define the minimum point and maximum point. But the good thing is, if you keep on one direction, if you keep tracking one direction, if that direction we have, what's it? Increasing of the objective function, of the value of the objective function, you go that direction, well, you can increase the value of that objective function, right? And on the opposite direction, you can minimize it. Okay, so you see that if we have the only objective function, we cannot define the minimum or maximum point, right? Imagine that, well, we have we have linear function. You go this way is the maximum, right? You go down this way, it's a minimum point. So if I give you only objective function, we cannot find the maximum, right? If we go on the right hand side, we increase it, then at infinity, we have maximum point. Okay, so always we need constraint. Okay, and once we have constraint somewhere, maybe, yeah, this area, this feasible region here, the maximum point is always at the corner, right? At the corner, at the vertex. Okay, that means if we can find the vertex or the corner point, well, the optimum point will be on any vertex. Okay, you just check the vertex and then check the value of the objective function at that vertex, and then, well, we can find the optimum point. Okay, let me show you the representation of the linear programming. For example, wow, for this one, we minimize f. F is our objective function, and f is a function of x1 to xn. Okay, multidimensional. We have n decision variable. So the objective function looks like, yeah, this function c1 x1, c2 x2, plus, well, c3 xt until cn xn. Okay, where c is constant. It must be constant, right? Because it's a linear function. Okay, for linear function, of course, you cannot have a term, nonlinear term, right? So for linear term, of course, you can have only constant term with variables. Okay, you cannot have multiplication of x1 and x2 or xi xj, right? Because that render the function nonlinear. Okay, and if we look at the constraint also, our requirement is all the constraint must be linear function. Okay, so if you, wow, this is a standard form where we have a11 x1 plus a12 x2 until a1n xn, okay, equal b1, okay, where b1 is also constant, right? And of course, while you may have question that, well, in some case, if we are dealing with inequality constraint, do we need inequality constraint here? Yeah, I can tell you that we can transform, we can render the inequality form to equality form. Okay, so the standard form we can write as a equality, okay, constraint. I will show you later how we can transform from inequality constraint to equality constraint. Okay, so we have a11 x1 plus a12 x2 to a1n xn equal b1. And of course, if we have more than one constraint, we can have a21 x1, a22 x2 plus, and so on to, well, until a2n xn equal b2. Okay, and finally, if we have n right? We have no. If we have m constraint, the last one can be am1 x1 plus am2 x2 plus blah 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 until amn xn equal bm. Okay, so the standard form we restrict the signs of all these variables must be positive. Okay, 0 or positive. And you see that it's quite long thesis to write such a very long function. So you see that we can write this one as a vector, right? So it can be written as C transpose X. Okay, and if we look at the constraint, of course, this is very easy to write as a AX equal B. So the structure of X must be vector, okay? And the structure of A must be A M by N, right? Because A is vector now. Okay, so you see that we can simplify all these representation by using matrix and vector like this. Okay, X is vector, C is vector, and A is matrix. Okay, B is also vector. But of course, those must be compatible, right? For example, can you tell me for example, X is a, just one moment. If X is 1 by, should we write 1 by N? No, it's N by 1, sorry. N by 1. If we write X as N by 1, let me write on this. Can I annotate here? Okay. X first. X is N by 1. Okay, it's vector, right? What is the size of C then? If we write, not something, 1 by N, right? 1 by N, no, it should not 1 by N, because you see that we transpose it here, right? C transpose must be 1 by N. So C must be N by 1 also, right? The same. You got my point? Okay, because if C is 1 by N, we have problem here. We can multiply C transpose with X, right? And the last one, what about A? No, A is metric. M by N. Okay, right? What about B? Yes, M by 1, right? Okay, now you get the point. Okay, all metrics and vector are compatible now. Okay, so for the standard form, we write the objective function in the form of minimization. If you want to maximize, it's very easy. You multiply with -1. Okay, then you can transform from maximize to minimize. Okay, and the next one, all the constraints are of the equality type. This is a problem. How can we transform from inequality to equality? For example, if we have a 1 x1 plus a 1 2 x2 plus until 1n x n lesser or equal b1. For the transformation, oh, what is this? One moment. Oh, I see. I annotated on Zoom. It's okay. So, well, how can we transform from inequality like this to equality? You know, all x is positive, right? Yes, we can add select variable to the left hand side. Because to guarantee that this one is less than b1, you add it with some positive number, you can transform lesser than or equal to equal. Example. Well, we have example later. Okay. All right. Yeah. Because you have two things two sides to compare, left hand side and right hand side. And it's lesser than or equal. Then this left hand side is less than right hand side, right? You add it with positive number, it will be equal. Yes, that makes sense, right? So that means you add one more variable for one inequality constraint, then you can transform the inequality constraint to equality constraint. Okay. And the next one, all the distant variable are non-negative. So here we have restriction that all in some case, you don't have restriction for some variable. For example, one variable you don't have a sign. It can be negative or positive. What to do? How can we transform it to the standard form? For example, we have x1 to xn, right? All x1 to xn minus 1 has a restriction on the positive side, non-negative. However, for xn, it is relaxed, no restriction on the sign. We have to convert it to the restriction form. Xn can be written as maybe x prime n1 subtract by xn prime x prime n2. Just let me write in the slide. Well, for example, we have xn without restriction. It's very simple. We can write xn. Write this way. Okay. You add extra variable, then you can assign the restriction on the xn1 and xn2. They must positive. Okay. Then you can transform the problem to the standard form. I think we have, it's okay. We have example later. For example, if we don't have, just a moment. In my example, x1, x3. Wow, x1, x, oh, positive. Let me check which. No. Okay. Show you. I have to write example now. How can I delete that or clear? Clear on drawing. Okay, good. For example, we have minimization of x1 plus 2x2 plus 3x3. Okay, and we have constraint. The constraint is x1 minus x2 plus 2x3 must be lesser or equal 5. Okay. X1 is non-negative. X3 is non-negative. Okay, we don't have restriction on the x2. Then we try to transform this problem to the standard form. Okay, the first thing we have to look at the non-negative sign first. We have x1 and x3, which are non-negative, right? However, we don't have x2, restriction on x2. So we write x2 as xa subtract by xb. Okay, and we have restriction that xa and xb must be positive. Okay, then the problem becomes minimization of x1, and we plus 2 of xa minus 2 of xb. Okay, plus 3x3. For the constraint, you see that we have to replace x2 by xa minus xb. Okay, that is the first thing to do. Minus xa plus xb, right? And then plus 2x3, right? Okay, and we add one slack variable. It can be s, okay, s1. It's become 5. Okay, then this is the standard form, and we have all x1 must be x1, x2. No more x2. xa, right? xa, xb, x3, and s1 must be non-negative. Okay. Must be. You cannot have negative slack variable. If it's negative, we have problem, right? We cannot guarantee that. We cannot change the lesser or equal to equal. Yes, yeah. We guarantee with this one. S1 must be positive. Well, of course, if you have greater or equal, right? Then you have to multiply everything with negative. The sign will be changed to lesser or equal. Okay. Yeah, we will deal it with that point later. Okay. Or you can, instead of plus S1, you can minus S1 instead. It is the same. Okay, because S1 is positive, then you minus S1, it's become from greater or equal, will be changed to equal. Yeah, for example, if we have x1 plus x2 plus x3, this is greater or equal, let's say 4, then you subtract it. This side, y s1. S1 is positive. Because S1 is positive, then yeah, it becomes equal. The same idea, lesser or equal. Okay, so move to the next one. So any linear programming can be expressed in a standard form, okay, by using these rules. The first one, maximization of a function is equivalent to the minimization of the negative of the same function. Okay, you multiply it with -1, and then you can transform from maximum to minimum. Okay. The second rule, an unrestricted variables can be written as the difference of two non-negative variables. Okay. Previously, I showed you already. The next one, a constraint in the form of less than or equal to. Okay. You transform it, you convert it by adding a non-negative select variable to the left-hand side. A constraint in the form of greater than or equal to can be converted by subtracting the non-negative select variable. Okay, instead of subtract, you instead of addition of the select, you subtract it. Okay. Okay, so now we deal with the algorithm to illustrate the idea how we solve the linear programming. We should start from the concept of gradient first. So consider the objective function, this objective function. If we want to maximize z function, okay, this function is in the form of Cjxj, okay, C1x1 plus C2x2 until Cnxn, okay. So for any value of the objective function where z1 does not equal z2, we obtain a different hyperplane, which is parallel to for the one obtained for z2. Okay, so while look at this function, for example, if z is 1, all the imagine that we are working on the 2-dimension problem. Well, for any x1, x2 that have a what's it equal the same objective function, it must be lie in this line, right? If the, for example, we have C1x1 plus C2x2, okay? This function can be the same. I mean, for example, can be, if this function is 0, we have a set of coordinate of x1 and x2 which have the same value of the objective function. And it can be like this, for example, this. And well, we can guarantee that this objective function must be 0 because it's past the coordinate of 0, 0. Right? If it passed the coordinate of 0, 0, that means, well, one variable is 0, then both variables are 0, then the objective function must be 0, right? Okay. And if we move to the next point, any point, the same idea also apply. For example, if the objective function is 3, we have a set of coordinates. Okay. Infinity coordinates, of course. This set contains infinity coordinates, but they all have equal objective function. Okay. Any point on this line have equal objective function. Okay. Also, we move further. We have a set of, well, coordinates that have the same value of the objective function. Okay. So we call this line as isoprofit line. Imagine that our objective function is profit. All the coordinates here lie in the same line, have the same profit. Okay. Or you can call it contour line. Okay, the same. And if we draw a direction which is perpendicular to the contour line, we have a vector of gradient. What does it mean? This gradient. This vector, this gradient, show you the direction that the objective function change. Right? Because it's gradient of that function. It must be, well, perpendicular to the contour line. Okay. So what does it mean? It means if we move this direction, we can increase the objective function. If we want to maximize the objective function, we should go this direction, right? If you want to minimize, you have to go opposite way, opposite of the gradient. Okay? This is analysis of the objective function. Okay, so if we look at some example, if we want to maximize x1 plus 2x2, okay, we draw gradient, this gradient of this function. How can we draw this, the gradient of this function, x1 plus 2x2? We can draw a vector passing origin and 1, 2. Where did I get 1, 2 coordinate? It's from the coefficient of the objective functions because it's 1, 2, right? So this direction is the gradient of this function. Okay. Huh? We want to draw the gradient. If you don't, well, believe me, you can draw the gradient by yourself. You can find the slope of this function. You can draw by yourself. It's the same. Okay. But the trick is you draw a line passing origin at coefficient 1, 2. You get the gradient. Okay. So if we move through this vector, this direction, we can increase the objective function. Okay. What about other direction? For example, this direction. Yes, of course, we can improve the objective function, but it's not the gradient. I mean, gradient means, well, you go that direction is the fastest way to improve the objective function. Okay. What about this one? This objective function minus 3x1 plus x2. This direction. Yes. Then if you want to maximize the objective function, you go this way. It is the fastest way. Okay. Or you want to minimize it, you go opposite way. Okay. This one also. Wow, the third one, minus 3x1 minus 2x2. Yes. The coefficient is minus 3 minus 2. So it's here. Drawing this line. It's the gradient of this function. Okay. And this is the gradient of this function. Okay. As I told you that if we have only the objective function, we cannot define the minimum point or maximum point. Because, for example, the first function, you go this way, of course. You get higher and higher value of the objective function. You go this way, decreasing the objective function, right? So finally, you reach infinity. And this way, you got negative infinity, right? Okay, so how can we use this idea to solve the linear programming? We have to draw the constraint. As I told you that, well, if we know the feasible region, we go, if we want to maximize, of course, we go on, follow the gradient direction. And then once you reach the last point, which is still in the feasible region, but it has the maximum value of the objective function, then you get the maximum point. If you want to minimize, you follow the direction of the opposite way of the gradient, right? Until you reach the last point, the final point that's still in the feasible region, you get the minimum point. Okay? Consider this figure. Imagine that we have 3 constraints. The first constraint limit our feasible region to the right hand side. Okay, this is the first constraint, right? So feasible region is this direction, this area, from this area. Okay, this side. Okay, and the second constraint, define the feasible region below this line, this part. Okay. And the third constraint define this area. Yeah, above the third line. Okay, so where is the feasible region? Feasible region is the intersect of all those 3 constraints, right? And then our feasible region is here. Okay. Okay. Any point lie in the feasible region, we call it feasible point or feasible solution. Okay. And it can be our solution, okay, because it's feasible. However, in order to find the maximum point, we have to follow the gradient. Let's say this is our gradient of the objective function. So apparently, where is the maximum point? The maximum point must be here, right? Because along this way, we improve the objective function and perpendicular to the gradient. Yeah, of course. Actually, it's perpendicular. However, the scale is not scale of x and y not equal. So, well, it's not perpendicular. Looks unperpendicular in this figure. Okay, but this is the last point. We cannot go beyond this, right? Because if we go beyond this, we step out from the feasible region. Okay. So the maximum point is here. Right? It's very simple and intuitive, I think. What about minimum point? Minimum point is here. This corner. Okay. Any questions? No, we move further. Okay, now consider the following linear programming problem. We still in the 2-dimension. Okay, we have only 2 variables, distant variables, x1 and x2. However, we have multiple constraints. The last one, this one, yes. Minimum point is here. This point. Wow, for this point, you see that the profit is around this, right? Because we know that, imagine that it's this contour is perpendicular to gradient, okay? If you want to maximize it, you move this way, right? So the last point, that the any point in this contour still in the feasible region is here, right? However, you move this way to minimize it. The last point is here, right? If you consider this point, of course, the objective function is around here. You can move further down. Okay. Okay, so to solve this problem, where should we start? We learned about graphical technique, right? The first thing, we draw the graph x1, x2. We draw each constraint. Okay, where is this is the first one. This is the first constraint. Okay, and it is greater or equal, so it should be on the above this line. Okay, if we look at the second constraint, 3x1 plus 4x2 must be less than or equal 12. We draw that line first, that function first, where is 2? This, yeah, this constraint. And the feasible region is below, right? Below this line. Okay. And the third one, x1 minus x2 less than equal 2. Where's the third one? Yeah, right. Yeah, we draw this one first, this line first, and then we check lesser or equal must be above this direction. Yes, this region. Upper. Okay, so we draw all constraints. And the constraint, this set of constraints form a feasible region here. A, B, C, D, E, F. Okay, the area having A, B, C, D, E, F vertices. Okay, then you draw the gradient. This orange arrow represents the vector of the gradient. The gradient is moved this way. The gradient moved this way. Okay. So where is the maximum point? Yes, it must be C, right? Okay. What about the minimum point? It should be F, right? Yes, because you go down this way. Okay. Hmm? Huh? Gradient here? What? What is your question? How do we define this? That yeah. Well, you draw a line passing origin and to 1. Okay. This one, right? Remember? The gradient of the first function is we draw the line passing origin and 1, 2, right? Mm-hmm. Okay. So it's really easy, right? As long as you can define the feasible region and you can draw the gradient, you can find the maximum or minimum. So for the graphical technique, just one moment. I should close this first. Okay. For graphical solution technique, the first step is graph all constraints and determine the feasible set first, feasible area. And then graph the gradient of the objective function. And then you shift the contour line or isopropyl line into the direction of the gradient of the objective function until you reach the last feasible point. Okay. Okay. And it is done. Let me show you 4 special cases. Not all linear programming have solution. Okay. We have 4 special cases. This one is the first case. No feasible solution exists. Okay. Imagine that our constraint here, we have this constraint x1 lesser than equal to x2 lesser than or equal 1 to x1 plus 5x2 is greater than or equal 10. X1 is greater than 10. X1 is positive, not negative, sorry. X2 is non-negative. And you see that the first constraint, where is the first constraint? X1 lesser than or equal to. Here, right? Lesser than or equal. Yes, this one. Okay, and because it's lesser than, it should be moved to the left, right? Feasible region. And the next one, X2 lesser than or equal 1. This line, right? It should be below this line. And we have 2x1 plus 5x2 must be greater than 10. And you see that it forms this area above this line, this line. Okay. Apparently, we don't have feasible region here because the intersects of those constraints are it's empty set. Okay. This is the first case. We don't have feasible solution because we don't have feasible region. Okay, we move to the next case. We call it unbounded optimum solution. In this case, if our feasible region, of course, in linear programming, our feasible region is polytopic, of course. And if this polytopic is not closed set, it's open this way. You see that? This example. The first constraint, minus 2, x1 plus x2 lesser than or equal 2 is from this line, right? Above this line. Okay. And the second constraint, x1 minus 3x2 lesser than or equal 3, it should be below the constraint number 2 here. Okay. And the next constraint is x1 must be non-negative. Okay. Above x-axis. And the last constraint, the fourth one, x2 must be non-negative. So it's here. And you see that this feasible region is not closed. It's open this way. Then, if our gradient lie between this, sorry, where is my cursor? Okay. Lies between this vector and this vector. That means the feasible, the gradient somewhere, this direction, or this direction. We cannot determine the maximum point. The maximum point is at infinity. Okay. However, if the gradient point to the opposite direction, or well, other direction, for example, this direction, of course, we can have maximum point. Okay, maximum point somewhere here, here, here. Okay, depends on the direction. Okay. Okay. So in this case, if our gradient point to this way, of course, we have unbounded optimum solution. This is the second special case. The next one, dual degeneracy. For dual degeneracy, for example, this problem, if at least one of its adjacent extreme point has the same value of the objective function, we call it dual degeneracy. Okay. And if dual degeneracy occur at optimal extreme point, then at least one alternative optimum solution exists. What does it mean? I will show you in the graph. Consider this problem. You see that our gradient is the direction that pass origin to 1, 1, right? And if we draw the first constraint is x1 plus x2 greater or equal 1. What happened? And the next constraint also x1 plus x2 lesser than or equal to. What happened? In this graph, it doesn't look perpendicular, but trust me, it's perpendicular between the gradient and the constraint. Why? Because if you look at the coefficient of the objective function, exactly the same with the coefficient of the constraint, right? So it should be in the same direction, right? That means this gradient is perpendicular to this constraint. So if you determine the maximum point, we move along this way, right? Along this way. And the last point is here. What does it mean? This point also has the same objective function, right? Because it's perpendicular, then this line, the constraint number 2, is the isoprofit or the contour of the objective function. Then we have infinity solution starting from that corner, this corner, to this corner. Okay, all solution lie in this constraint, lie on this constraint, can be our solution. Okay, this case we call dual degeneracy because we have multiple solutions with the same objective function. The next one is, I told you for special case, right? So this one, the fourth one, we call it primal degeneracy. In this case, we have only one solution. Okay. If more than n hyperplane intersect at one point, and that point is the solution, we have only one solution. However, that point defined, over-defined by multiple constraints. Okay. For example, look at this constraint set. I draw that constraint in the graph. Okay, our constraint, those three, the first three constraints, 1, 2, 3, define the feasible region here. Okay, down here. If our constraint, no, objective function point to this direction, the maximum point is here, of course. However, normally, in order to identify this point, we need only two constraints. But in this case, we have three constraints defining this point. Okay, we call it primal degeneracy. Okay. Hmm. Well, imagine that you are working on debottlenecking the problem, your process, and you identify that this line is the capacity of your process. For example, this line is capacity of your process, and this line is maybe the availability of the raw material, and the next one is the capacity of something, I don't know. Then your boss asks you if what to do to improve the production. Then, well, you give solution to your boss that, well, I identify that this is the maximum point here. And you don't know exactly. We have 3 constraints define this point. And you suggest, you report to your boss that, of course, we have to change the pump, the capacity of the pump, define this point. And also, well, the other one, I don't know which constraint. You neglect the last one. You order a new pump, of course, you can shift the constraint to the right-hand side. And you think the solution will be changed if you just move this constraint to the right-hand side. No. No, it doesn't change because you, for example, this is a pump, right? The blue is pump, and the orange is the heat exchanger, okay? And this one can be reactor, for example. You don't know that reactor also define the constraint here. You report to your boss that, wow, we should buy a new pump. Then the constraint move to the right-hand side. However, the maximum point is still the same because it's defined by these 2 lines. Okay. Okay, this is a case of primal degeneracy. For this one, if you analyze the process, then you identify that both reactor, heat exchanger, and pump, then you have to buy all these 3 things at the same time, right? Okay, it's good to have graphical solution because it's really easy to understand, right? It's intuitive technique. However, the limitation of the graphical technique is we cannot draw 3 dimensions. We cannot draw 4 dimensions, right? So we use algebraic solution technique. However, the idea is the same, okay? We look at the vertex of the feasible region, okay? So the first thing, I will show the canonical form with non-negative right-hand side first. We need this form for the algebraic solution technique. For example, if we want to maximize this function, C1x1 plus C2x2 until, well, Cn xn, okay? And the constraint is, can be inequality, okay? We call it canonical form, this form, we call it canonical form. It's cone, it's from the cone. And for representation, the notation, if we want to save the space, of course, we can write this problem as a using metric, okay? And we call metric notation. It is the same problem. Of course, we haven't convert anything, okay? The inequality is still inequality here, okay? Then we have to convert this problem by using slack variable and also while using the technique we learned before, okay? For any inequality lesser than or equal, we just add the slack variable and then we can transform it to equality form, equality constraint, okay? So the metric notation of this form, it's just like this, okay? AX plus IS. What is I? I is identity matrix, okay? And B is vector, of course. This is the fundamental of the most simplest algorithm to solve linear programming. We call it simplex method, okay? You can guess from the name because the name is simplex method, then this is the simple one, okay? The first one, we have to guarantee that all xi must be non-negative, okay? If you have unrestricted sign variable, you replace it with subtraction of two variables and it's okay. And for equality constraint, use two-phase algorithm. We cannot deal equality constraint at this point, okay? Just skip it first. Later, I will tell you how to deal with the equality constraint. The next one, all constraint must be in the form of lesser or equal, where B must be positive. No, not positive, non-negative. Must be non-negative, okay? If you cannot convert to this form, we need two-phase algorithm, okay? Hold on. We will do it later once I explain the simplest one first, okay? Then you transform all the inequality constraint where bi is positive, it's not negative, sorry, it's not negative, by using slack variable. You add slack variable to the left-hand side and then, well, it's convert to equality constraint, okay? So our table looks like this. We have n decision variable, and because we have m constraint, right? Each inequality constraint require one slack variable. Then, because we have n inequality constraint, then we need m slack variables, okay? We have n variable first, A matrix, x1 to xn. And in the process of transformation, because we don't have equality constraint, all the constraints are in this form, where bi is non-negative, okay? Because we have m inequality constraints. Then, because one constraint needs one slack variable, if we have m constraint, we need m slack variable, okay? And you see that the size, the dimension, this one is square metric, right? because we have m constraint and we have m slack variable. So here should be square. Okay? And it must be identity matrix because for the first constraint, we are S1 and the rest becomes 0, right? The second constraint, the first one, the coefficient of the first S1, 0. We add S2 on that constraint. Okay? Okay, good. You see that our degree of freedom is n. Right? Because the number of variable in this case is, what is the number of variables? Cartoon. What is the number of variables? N plus m. Right? The original one, we have n variables and we have m slack variable. So totally we have n plus m variables. And we have m condition. Only m condition, right? Each constraint. Totally, degree of freedom becomes n because n plus m subtract by m. The degree of freedom is the number of variables we have subtract by the relationship we have. We have m relationship, right? M constraint. So it is n plus m subtract by m, right? M cancel it out. So the degree of freedom become n. So what does it mean? You cannot solve this system of equation because degree of freedom is greater than 0. Okay. How can we solve this problem then? This system of equation. How can we solve it? We have to define at least, we have to define n variables, right? Because degree of freedom is n. So n variable out of n plus m must be defined, right? You have to guarantee that the degree of freedom must be 0. Okay? So we separate those n plus m variable. We categorize the variables as basic variables and non-basic variables. Okay? The number of basic variables is m, and the non-basic variable is n. Why? Because we're going to force all the non-basic variable to be 0. What happens if we set all the non-basic variable on n variable to be 0? Then the degree of freedom becomes 0, right? Because degree of freedom is n, right? And then we set n variable to be 0. Okay, so you select n variable to be non-basic variable, and you set those non-basic variable to be 0. You can solve this problem. Okay, so the idea is we formulate the problem, this form, and then we find the basic feasible solution. Okay, and then we compute the value of the objective function. Later you can read and try to understand what I wrote here, but I'm going to explain the algorithm to you, okay, in a more easier to understand. remember that our algorithm, the simplex method, we must start from the basic feasible solution. Okay. This is iterative. Wow, full of text. Later you can read it by yourself. I will show you, explain you from the example. We start from this problem. We have objective function 40x1 plus 50x2 plus 100. And the constraint is, wow, the first constraint is 2x1 plus x2 lesser or equal 12. And so on. We have three constraints here, right? For this non-negative constraint, we don't consider in this algorithm, but it is required. Okay. We construct a table. Okay, table here. The first part, x1, x2. Okay. You put the coefficient of each variable in the table. Okay. 2, 1, right? And during the process to convert the first constraint, yeah, you need S1, right? So you need the coefficient 1 in S1. However, you don't have S2, S3, so the coefficient must be 0. Okay? And the right-hand side is 12. Okay? And the second line, the second row, we have -4 here, 5, and 0, and S1. Oh, no, not really. 1 of S2, and then 0. Okay? And the right-hand side becomes 12, 20, right? And from the third constraint, we have 1, 3, right? 0, 0, and 1. Because we add S3 here, select variable here. Okay, right-hand side, it's 15. Okay, and at the last line, you add the coefficient of the objective function in the minimum form, the minimization form. It is -40 and -50. Okay. And because you don't have, wow, the right hand side become 100. Okay, because from here, if we set to be 0, then wow, to make it equal 0, wow, this one must be 100, right? Yeah, this is a minimum form. Okay, so we have to remember that we separate our variable to be basic variable and non-basic variable, right? And what we set all the non-basic variable to be 0. Okay. What is the number of the basic variable? The number of basic variable must be 3, right? Because the number of basic variable equal m. And m, in this case, we have 3, right? At the first place, of course, we use the select variable to be basic variable. However, it will be changed later. We are talking about the number of it. Okay? And the non-basic variable, the number of non-basic variable, it's 2. What does it mean? To solve this table, we have to set non-basic variable to be 0. Okay? And at the starting point, if we set x1 and x2 to be 0, to be non-basic variable, because we need two variables to be non-basic variables. You set x1 and x2 to be 0. What happened? You see that from the first line, you don't care about x1, x2, right? Because we know that x1 and x2 are both 0. So S1, the value of S1 is, what is the value of S1? 12, right? Because this term becomes 0, right? 0, 0. Then S1 must be 12. Okay? And from the second line, x1 is 0, x2 is 0, S2 must be 20, right? And this line, again, is 3 is 15, right? And look at the objective function. This 0, 0, and starting point is 100. Okay? Our objective function is 100. Okay? Remember that always we start from the basic feasible solution, and this point 0, 0, x1 is 0, x2 is 0. This is s1, s2, s3. This point is feasible. It's okay. How do we want? Well, you want to improve the objective function, right? Because we want to minimize it. Can you tell me how to minimize this problem? From this table, you see that now x1 is 0, x2 is 0, right? We have certain value of the objective function. It's 100. It's, wow. Apparently, you look at the coefficients. What happened if x2 increase? Because the coefficient here is negative. What happened if we increase the value of x2? Right. Okay. So it's straightforward that we should increase x2, because at one iteration we can increase only one variable. Of course, you can increase x1 and you can have smaller objective function, which is good, of course. However, if you increase 1 unit of x1, you can decrease 40 units of objective function. However, if you increase 1 unit of x2, you can decrease 50 of the objective function. Which one is better? This one, right? Because it's more negative. So in the next round, next iteration, we will introduce x2 as our basic variable, because at each iteration, non-basic variable will be forced to be 0, right? So we introduce x2 to be our basic variable in the next round. Okay? But the problem is, if we introduce x2 to be our basic variable, we have to get rid of one current basic variables, right? Currently, we have 3 basic variables. They are s1, s2, s3, right? If we want to introduce x2 to be basic variable in the next round, we have to remove, either x1, s1, s2, s3, one of them. Which one should be removed? to judge which one to be removed, we look at the ratio of B over A. Okay? Because we're going to introduce this one, right? So we divide B, all this B, by A in this row. Why? Because next round, we're going to increase X2, right? Okay? So you have to look at the ratio of B over A, because X2 is increased. You look at the coefficient of A in this X2 column and find the smallest positive of B over A, because it defines that row we can increase largest value of X2. Okay? So you, well, find the ratio of B over A. This is 12, right? This one is 4. And this one is 5. So in the next round, we should remove S2 and introduce X2. Okay? Look at the graphic. Yeah, we have only 2 variables, so we can draw it. We're starting from this point, which is our feasible, inside our feasible region, right? This point, we know it because it's 0, 0, right? This is 0, 0. And what is the meaning of S1, S2, S3? S1, S2, S3 is the slack variable. Is the variable defining the distance from the current point to the constraint. Okay? It is clear because we add those values, those slack variable, and then constraint becomes equality, right? From this point, where is S1? I don't know which one is S1. But anyway, we add certain value. It's move this point to the constraint, right? Yeah, that is the meaning. Yeah, we move from this point to this constraint by adding slack variable to it. Also, well, the other one, because I don't know which one is the S1, S2, S3. Yeah, but it is the same meaning. S1, S2, S3, it's, well, the distance from current point to the constraint. This constraint, this constraint, and this constraint. Okay? Okay, now we identify that this is the point where we work in the next round. Okay? So you see that for all basic variable, we convert the table such that the coefficient of the basic variable becomes 1. Okay? At the beginning, we did nothing because the coefficients are 1, right? This 1, 1, 1. Okay. Then S1 is 12, S2 is 20, S3 is 15, right? But then for the next round, if we work with X2, then our target is we have to convert this table such that this element must be 1. Okay? How to make this element to be 1? Divide this row by 5. Okay? So becomes -4 over 5 is 1, 0, 1 over 5, 0, and 4. Okay? What else should we do? The next one is, remember that when we find solution, yeah, solution S1, right? We know that X1 and X2 become 0, right? Then we know the solution, the value of S1. However, if we move, if this one is not 0 anymore, right? Because X2 is not 0 anymore, we have to convert, we have to transform this table such that this element become 0. This element also becomes 0, and this element becomes 0. Okay? We allow only this element to be 1. The rest must be 0. How to do that? How to make this 0? Easy. We subtract each element by this row. Okay? So what we have here, we subtract the first row by the second row. Okay? So it becomes 140501, and then 1 minus 10508. Okay? And this line we do nothing on this. And for this one, for the third row, we have to multiply this row by 3. Okay, all elements in this row by 3, and then we subtract the third row. Okay, so it becomes this 170500 minus 30513. Okay, you got the idea? Now we look. Now what is the solution? Our solution now, we have S1, X2, S3, right? As basic variable. So X1 become, X1 is 0, right? Because X1 is non-basic variable, it must be 0. And what about X2? X2 is 4, right? Yes, this one is 4. How about S1? S1, 8, right? S3 is 3. So now we are at this point, 0, 4, 8, 0, 3. Okay? We move from origin to this point. Okay, we move from this point to this point. Are you ready? And you see that this one, the second constraint, S2, is our non-basic variable, right? And the value is 0. What does it mean? The slack variable for the second constraint is 0. What does it mean? The slack variable is 0 at that constraint. Remember that originally the constraint is lesser or equal, right? And we add slack variable to it. And if the slack variable becomes 0, what does it mean? That constraint is active. The constraint is active means, well, it's equality constraint. It's changed to equality constraint. Or the solution, the current solution, it's at that constraint. Okay? Which is true, right? Because now we are at this constraint. So this line is the second constraint. Okay? So look at the table again. Now we look at the coefficient of the objective function. Now we have minus 80, 0, 0, 10, 0, and 300. Yes. You look here. We add S2, right? And S2 is 0. What does it mean? Yeah, become equality. Yes. Because we add 0 to it. And it's, yeah, it must be at that point. Equality. Because it's lesser or equal. If we add slack and the slack is 0, that means, well, minus 4x1 plus 5x2 is 20 at that point. Okay, so we look at the coefficient of the objective function. We see the negative on x1. What does it mean? If we change the value of x1, if we increase the value of x1, we can further decrease the objective function, right? Then what about S2? This one, 10. If we increase S2 instead of, yeah, we introduce S2 in the basic variable, or S2 increase, we increase the objective function instead, right? So we don't go this way for sure. We go this way, right? So the next round, we should introduce x1 as our basic variable. Okay. And what should we remove from our current basic variable? We look at b over a. The smallest positive b over a is this line, S3. So then in the next round, we should introduce x1. And we should remove S3 from the set of basic variables. Okay? Okay. Again, we transform the table such that the coefficient here, x1 here, become 1. Okay? And we transform the table again such that the coefficient here and here, also here, become 0 by using the same technique. Okay? For example, here, in order to make this the first element to be 0, we multiply 14 over 5 to this row and then subtract with the first one, the first row. Okay. Also, we multiply minus 4 over 5 to the third row and subtract the second row. Okay. Then this one becomes 0. And the last one, we multiply minus 80 to the each element, this row, the third row, and then we subtract by the fourth row. Okay, so we get 0, 0, 1, 0 here in the first column. Okay, and you see that the second column we have 0, 1, 0, 0. Okay, the last one, because our basic variables are x1, x2, and s1, right? Okay, so now we move to what is the current point? Our solution now, the basic feasible solutions are the basic feasible solution at this iteration is 1, 1. No, not 1, 1. Sorry, 15 over 17, right? And the x2 is 80 over 17. S1 is 94 over 17. and S2 is 0, S3 is 0. Okay? We are at this point. Hmm? It's non-basic variable. They are non-basic variable. Non-basic variable must be 0. You see it at each iteration. We start here. The basic variable is S1, S2, S3, right? They have value. But non-basic variable is X1 and X2. Non-basic variable must be 0. If you don't set them to be 0, you cannot solve the problem. You cannot solve the equation. It must be 0. Okay? Okay, so we are at this point. And you see that the slack variable for the second constraint and the third constraint are 0. Here, 0. What does it mean? This point, the second and the third constraints are active, right? Yes, they are active because this is the corner, which is the intersection between the second and the third constraint. Okay? However, this point is not the minimum point yet. Why? Because if we look at the coefficient here, we have S2, which is negative coefficient. Okay? S2 is still negative at this point. What does it mean? If we introduce S2 back to the basic variable, we can further decrease the objective function. Okay? So you have to consider B over A. Which one should be removed? This is the smallest positive B over A. Okay? So for the next round, we introduce S2 to be our basic variable, and we remove S1 from the set of basic variable. Okay? We use the same technique. We render the table such that this element become 1, the other element in the same column become 0, 0, 0. Okay? Okay. We change it to be 1 first, right? And then we render the table again. Now we reach this point. Our basic variable now encompass x1, x2, and s2. Okay? x1 is 21 over 5. x2 is 18 over 5, right? Where is x1? x1 here, right? 21 over 5. x2 is 18 over 5. s1 must be 0 because it is non-basic variable. And S2 is 94 over 5. S3 must be 0. We are at this point. We move from this point to this point, okay? And at this point, S1 and S3 are 0. suggesting that the first constraint and the second, the third constraint, and the first and the third constraints are active. Okay. You see that this is the minimum point because all the coefficients of the objective function are positive. Okay. What does it mean? If you introduce S1, the objective function will be increased. You introduce S3, objective function will be increased. Okay. Any questions? Also from Zoom. Any question? I check our participants first. Let us break for 5 Okay, should we continue? We have one more example. Actually, wow, 2 or 3 more, but we look at this second example first. Again, this one we have is maximization. Of course, we transform it to minimization. Okay. Oh, let me check my microphone first. Yeah, it's cool. Okay. Well, we minimize it, right? Minimize x1 minus x1 minus x2 x2 minus x3. And for the constraint, the first constraint, we don't have problem at all. We just add slack variable, one slack variable, because on the right hand side, it is non-negative. And for the second constraint, we multiply by -1. So it becomes 2x1 minus x2 plus 5x3 lesser than or equal 6, right? And the next one, it's all right. Yeah, we have to add slack variable also. Okay. And the next one, we add slack variable. Okay. So we transform it to the right hand side first, and then yeah, we write down the tableau. At the first point, at the initial point, because we have 6 variables and we have only 3 relationship. So we need 3 basic variable and 3 non-basic variable. Okay. Of course, we start from S1, S2, S3, our basic variable. Okay. So the first point, we are at 0, 0, 0, 2, 6, 6. Okay. Is X1, X2, X3, S1, S2, S3. Okay. Remember that we must start the algorithm when the basic feasible solution, when the point we start the algorithm must be feasible point, basic feasible solution always. Okay. Okay. We look at the coefficient of the objective function. This column is the most negative one. Okay. So we introduce x2 to the set of basic variables in the next round. And we perform B over A, which row show the most smallest positive. We select that row, this one, right? This is 2, right? We don't select this row because 6 over -1 becomes negative. We don't select negative. We choose only positive, smallest positive. The third row is 6. So we select this row. So it should be 1, 0, 0, 0. Okay. We perform the elimination, Gauss elimination. Yeah. We perform row operation and then becomes 1, 0, 0 here. Okay. Over here, we have x2 as our basic variable. S2, S3, right? For non-basic variable, we have x1, S2, oh no, x1, x3, and S1. Okay, so the current point is 0, 2, 0, 0, 8, 4. Again, because this is negative, the most negative coefficient. So x3 should be introduced to the set of non-basic variable. And we check B over A. This one is 2, right? 8/4, it's 2. This one is negative. We don't use negative. And this is 2. We select either one. We select this one. It's okay. So we introduce x3. We remove s2 from the set of basic variable. So we transform. We render it such that this element 0. This one is 1, 0, 0. Okay. We perform row operation again. It's 0, 1, 0, 0. Okay. So the current point is 0 because x1 is non-basic variable, right? So it must be 0. And x2 is 4. X3 is 2. And S1, S2, S3 is 0, 0, 0, respectively. Yes. X1 basic variable, it's x2, x3, and s3. Yes. Though s3 is not basic variable, but the value is 0. Okay. No problem. Okay. What about this problem? The next problem is, minimize. So we don't have to convert from maximize to minimize because it's already minimized. And for this one, just we need S1, right? Select variable. And this one, we need S2. Okay. We construct a table. We have 4 variables, X1, X2, S1, S2. And our basic variables are S1, S2. Okay, S1, S2. The most negative coefficient, this column, X1. So B over A is 1, B over A is 2. Then here, we introduce X1 next round. We remove S1 next round. So this column must be 1, 0, 0. Okay, we use row operation, and then we are at 0, 0, 1, 6, right? And then from row operation, we got 1, 0, 0. This column. The second column, we don't care about it. Yeah, it's still non-basic variable. It's non-basic. S1 also non-basic variable, but S2 it's basic variable. So at this point, we have X1 and S2. X1 is 1, right? X2 is 0. Okay, we are at 1, 0. We move from here to here. 1, 0. And 0, 3. Okay, so this point, this column is the most negative coefficient, right? So X2 will be introduced into the basic variable set next round. And we remove S2 from basic variable set. So it should be 0, 1, 0 next round, in next round. 0, 1, 0. Okay. BOA. This is negative. Yes. This is only positive here. Okay. So we end up with this table. What is the problem? We see that S1 should be introduced to the basic variable next round. But the problem is we cannot remove X1 or X2 from the basic variable because the coefficient B over A are all negative, right? So we cannot further use the algorithm. All coefficients are negative. we should stop here. And in this case, it signifies the unbounded optimal solution. If you look at this one, we stop at this point, and we can further decrease the objective function. However, we cannot go to the next point because they are unbounded. Okay. And you see that from the algorithm, it signifies that, well, we cannot further move to the next point. Yes. Yes. Minimize, we find the most negative. Yes. Minimize. Always minimize. You see, we convert from maximize to minimize already. Every time we work on minimize problem. Okay. So the next topic is two phases of the simplex method. Previously, we learned the simplex algorithm. However, we have some limitation. The first limitation is we cannot deal with equality constraint. Okay. Also, we cannot deal with the constraint where the right hand side is negative. Okay, every time the right hand side must be non-negative. Okay, and the next issue is we have to start the algorithm from the basic solution. We cannot start the algorithm from the the infeasible solution. Okay, so we deal with two-phase algorithm. We use two-phase algorithm to solve such a problem. The first one, we arrange the original system so that all constant terms, the right-hand side, B, are positive or 0. Okay. Then introduce a set of artificial variable. Okay. For example, for this one, if we have equality constraint, we introduce new variables we call artificial variables, E1. Okay. We arrange the inequality constraint such that the negative, the right-hand side constant is non-negative. No matter this is greater or equal, it's all right. Then once you have greater or equal, you subtract the slack variable to this constraint. Okay, minus S1 instead of plus S1. And at the same time, we need artificial variable also to handle this greater or equal inequality constraint. Then, from the name of the algorithm, what is the name of the algorithm? It's two phases, right? We have phase 1 and phase 2. The aim of phase 1 algorithm, we find the feasible solution, not to minimize the objective function. Okay, so we have to define one variable. We call it W, which is the sum of the artificial variables. All artificial variables, we sum up, and we set this function W is a sum of E1 plus E2 and so on. Okay, so what that is mean? You see that our W is the sum of artificial variable, right? And artificial variables, we use it to handle equality constraint. And this greater or equal constraint. So we try to minimize the W function, right? To find a feasible solution, because once we we force this W to be 0, what does it mean? It means we get the feasible solution already, and we will use those feasible solution as a starting point for the phase 2 algorithm. Okay, so remember that we must start from a basic feasible solution. Okay, phase 1 deals with the finding a feasible solution to start the main optimization process in the phase 2. Okay, what does it mean? It means that if the problem is already feasible to begin with, phase 1 can be skipped, right? Okay, so I will explain the algorithm from the example. Imagine that, consider this problem. Minimize 2x1 plus 3x2 plus 2x3 minus x4 minus plus x5. Okay, we have two equality constraints. So we have to add E1 and E2, right? We add E1 and E2. Yes. We will, in the phase 1 algorithm, we try to find the point where E1, all the summation of E is 0. If you have E1 is 0, E2 is 0, you can find, you guarantee that that point is feasible. Okay. Okay, so from the first one, we add E1. From the second one, we add E2, right? And from the objective function, we have 2x1 plus 3x2 plus 2x3 minus x4 plus x5 minus f becomes 0. Okay, and from the definition of the W is E1 plus E2, right? So E1 plus E2 minus W must be 0. Okay, so we see that we have E1 and E2 in the last line. We substitute E1 and E2 by using the first and the second expression, the first and the second equation. So we get this. From the last line, you see, we sum the first and the second line together. Okay, and substitute, we obtain the last line. Any questions? We substitute the first and the second in the last one. You get this one. Pardon? X1 is minus, which one? This one? No, it's 3x1 minus 3x. Why is it minus? Yes. Yes, because you substitute E1 in E2. E1 becomes, wow, minus 3x1, right? Minus 3x1 plus 3x2 minus 4x3. Yeah, you. And then this is minus x1. Yeah. Okay. Yes. And from this expression, we construct the table again. Okay. This x1, x2, x3, x4, x5, E1 and E2. Okay. While the first and the second one are quite straightforward. 3 minus 3, 4, 2. Yeah. 3 minus 3, 4, 2, minus 1, 1. Okay. And 0. The second line also straightforward. The third line, yeah, 2, 3, 2, minus 1, 1, minus 1, 1, and 0. Okay. And the last line, minus 4, 2, minus 5, 0, 0, and minus 2. Okay. The aim of the first phase is to guarantee that W is 0. Okay. But the same idea. We have to, what's it? Separate the variables to be basic variable and non-basic variable. In the first step, we choose E1 and E2 to be basic variables. Okay, because the coefficient is 1, 1, right? This coefficient is 1, 1. We set all other variables to be 0 because they are non-basic variables. Okay, so E1 is 0, E2 is 2. Okay, we find the non-negative, no, not non-negative, the most negative one, the column, and then we introduce this one, x4, to be our basic variables. And what to remove? Again, we perform B over A. The same procedure. Okay. So this column, of course, you can choose x3 instead x4. Okay. But in my case, I choose x4. Okay. So we have to transform this table such that we have this column as 1, 0, 0, 0. Okay. It's 1, 0, 0, 0. Okay. And the next round, the next iteration, this column is the most negative. Okay. So we need to introduce x2 to be our basic variable. Okay. And this is negative. We remove that. We don't consider removing x4. Okay. We remove E2 instead. And we render this table such that we have 0, 1, 0, 0. Okay. And this is the result. We have x4 and x2 as basic variables, and the rest are non-basic variables. And you see that at this point, W becomes 0 already. That means E1 and E2 are 0. Okay. Now we have a basic feasible solution already because W already 0. Okay, then we can perform the phase 2. Mhm. For phase 2, because we don't consider this W anymore because we have already get the feasible solution already. Okay. Also E1 and E2, we don't consider them anymore because E1 already and E2 are 0 already. So we remove from our table. Okay, we just remove this line and this column and this column. Okay, we obtain this table. And if we look at this table, this column is the most negative one. It's not the most, yeah. It's the only one which has negative coefficient. So x5 will be introduced into the basic variable set. And we remove x2 because this is the smallest positive b over a. Okay. This is 4 by 5, right? But this is 2 by 6 by 2, which is 3. Okay. So we use row operation and render this table such that this element is 0, this one is 1, and this element must be 0. Okay. 0, 1, 0, right? So we end up with this table, okay, where our basic variables are x4 and x5. And this is the solution because all the coefficients are positive. We cannot further decrease the objective function. Okay. Zero. You cannot remove the objective function. Which one? This one? Which one? This one? You cannot remove the objective function. Hmm? Wow, you don't have to write this. You don't have to write this. It gives you nothing. It's just make you confused. I don't write anything here. Yes. You don't have to write it because it's the same. Just to remind it. Just to remind us, we start from this. You can write f. Well, you see that under our algorithm, we don't use this value, right? You can, well, write f is okay. You can, well, you can skip it, whatever you want. Okay, now we move to the next We stop here already, right? Okay, we move to the next example. We want to maximize this objective function. Of course, because this one is maximized, we have to change it to minimize, right? 2x1 plus x2. Yes. Okay. And for the first one, the first constraint, because we have non-negative right hand side already, so just plus s1 is enough. And for this one, again, just plus s2. Okay. Add the slack variable. But the second one, you see that we arrange this one already. We have non-negative right hand side. However, this one is greater or equal. So we should subtract by slack variable, subtract S3 and plus E1. Then we start from the two-phase algorithm. Okay, so we define W as E1. Okay. So E1 minus W becomes 0, right? And we substitute the third constraint to E1 here. Okay. So we obtain this line. From this one, we construct the table, the tableau. The first and second row are quite straightforward. The third one also straightforward. -2, -1, 2, yes, 0, 0, -1 and 1, right? And where is it? The objective function is 2, 1, -5, right? 2, 1, -5 in this form. 2, 1, -5, 0, 0, 0, the rest. And the last one, minus W. 2, 1, -2. Okay, 2, 1, -2, 0, 0, 1, 0. And the right hand side is -4. Okay. So we perform the phase one first. Okay, look at the column of x3. We introduce x3 to basic variable and test b over a. This one is the smallest. So we remove e1. So we obtain this tableau. And you see that w becomes 0 already. Okay. Once w becomes 0, then we can start phase 2. We remove the last row and this column, E1 column out. Okay, we got this tableau. And from this table, of course, x1, the coefficient of x1 is the most negative. So we introduce x1 to the system, to the basic variable set. And we remove s1 because this is the only positive b over a. Okay. So we render this tableau such that we obtain 1, 0, 0, 0. Okay, 1, 0, 0. We obtain this tableau. The next step, we introduce x2 and we cannot introduce x2 because if we consider x2, all the coefficients are negative. Okay, we consider s3 instead. Okay, we introduce s3 and we remove x1. Okay, and then we end up with this tableau. The only negative coefficient is x2. We remove x2 and we introduce s2. Okay, we got this. And Well, still, all coefficient, we have negative coefficient for objective function. However, the coefficient of x1 in each constraint are negative. So we stop here. And remember that when we have this similar situation, this case is unbounded optimum solution. Yes. This one, this example. Hmm? For this one, right? Yes, we just finish. Here we have solution because all the coefficients are positive, right? The coefficient of the objective function are positive, then that means, well, we cannot further decrease the objective function, right? That means it's already minimum. However, in this solution, in this example, we still have negative, and it suggests us to introduce x1 to the basic variable. However, we cannot remove any variables out because all these are negative. It signifies the unbounded optimal solution. Okay, so we have another example here. Well, I believe that you are quite familiar with the simplex method. So we go, well, I explain you briefly about that. The objective function is minimum already, so we don't have to change the objective function. And the first one is okay. Yeah, just add the slack variable plus s1, right? The second constraint is also okay. Just add slack variable. And the third one, we have problem because once we have positive, non-negative at the right-hand side, the relationship here is greater or equal. So we have to add, subtract by slack variable and add E1, which is our artificial variables. The fourth one also the same, yeah, the same idea. We subtract by slack variable and add artificial variables. Okay, so we define W. W is the summation of E1 and E2 only. And we have E1 plus E2 minus W becomes 0. Okay, we substitute E1 by the third constraint and E2 by the fourth constraint. Okay, then we obtain this constraint, this expression. Okay, the last line. From this 1, 2, 3, 4, 5, we construct the tableau. Okay, it's quite straightforward. For the objective function, of course, it's 5, 2, 0, 0, right? It's 5, 2, right? And the last line, we have minus 4, minus 5, minus 4, minus 5, 1, 1. Okay, this is minus 7, which is on the right hand side. Okay, from here, we start from this the y column because it has the most negative coefficient, right? This is minus 5. Okay, and we look at the b over a. We remove E1, of course. So our target is we render this table such that we have one, this column becomes 1, 0, no, 0, 0, 1, 0, 0, 0. Okay. Yes, 0, 0, 1, 0, 0, 0. Okay. And from here, we still have negative coefficient here. So we introduce x1, no, not x1, x, and we remove e2 from the basic variable. Okay. So we render this table such that we have 0, 0, 0, 1, 0, 0 column. Okay. 0, 0, 0, 0, 1, 0, 0. Okay. Now we have, this table. And W becomes 0 already. So we can remove this row, W row, and E1 column, E2 column. Then we start the phase 2, okay, from here. And you see that if we look at this, phase 2, we already reached the minimum point because we don't have negative coefficient anymore. We cannot further reduce the objective function. Okay. You learn the concept of simplex method for, what's it? Two-phase algorithm. Okay. Remember that always we start from feasible solution. So for the two-phase algorithm, the aim of the phase 1 is to find the basic feasible solution, right? Okay. We have 20 minutes more. I will explain about duality. Duality algorithm, well, if we look at the constraint, we have a set of constraints at A11 x1 plus A12 x2. Yeah. The right hand side is B1, B2. Okay. This constraint. Okay. And the objective function. The duality constraint is from this set of problem, we can transform this problem to this problem. You see that on the right hand side, we have B1 to Bm, right? However, the duality of this one becomes the right hand side is a vector of C1, C2 to Cn. Okay. And the coefficient of the objective function consists of B1, B2 to Bm. Okay. And the matrix A, well, exactly the same. Not the same, sorry. But it's A11 to AM1. It's transpose of the original problem. You see that the first column here is A11 to AM1, right? But the duality of that problem, the row, it's A11 to AM1, okay? So the matrix A is transpose of the original problem, the primum problem, and the vector, the B vector becomes C vector, okay? We call it's the duality. This problem and this problem, it's what's it? Duality of primal, okay? And again, if you transform this one, we call it primal problem. Primal, we transform primal to obtain duality, and you transform it again, you will obtain the duality of it. Okay, primal to dual, you transform again, it becomes primal. Okay. And the next one is in the primal, f is to be minimized. However, the objective function of the duality is to be maximized. Okay. Now we compare between primal and duality. On the left hand side is a minimization of this objective function. It's summation of the Cixi, right? However, in the duality problem, it's a Yibi instead. Okay. And we transform the constraint, okay, from C here to B here, right? C here to B coefficient. And B here becomes C, okay, which is the original coefficient. Okay. Do we have, yeah, this is the example. If we have this primal problem on the left hand side, you can transform this problem to this problem. Okay, from primal to duality. Okay. You see that the number variable appear in the primal is different from the dual. Okay. In the primal variable problem, we have two variables, right? And the number constraint is 4. However, the duality, we have 4 different variable, but only 2 constraints. Okay. So let us discuss about the property of the duality first. The first one, the dual of the dual is the primal. Okay, as I mentioned to you. If both primal and dual problems has feasible solution, both have optimum solution, okay, and minimum f is maximum p, okay, minimum of the primal objective function is the maximum of the dual, okay. And the third one, if either the primal or dual problem has unbounded solution, the other problem is infeasible. Okay. So if you solve one problem and you found that it's unbounded optimum solution, if you take duality of that problem, the duality of that problem is infeasible. Okay. The opposite way also apply. If you consider the primal problem and you found that the primal problem is infeasible, the duality of that problem is unbounded optimal solution. Okay. So let's, well, another example. If this is our primal problem, maximize 2x1 plus x2. Okay, we have 2 constraints. Okay. And the optimum solution is at 1, 1. Okay. Assume that I solved this problem already and I got the solution already. The solution is 1, 1. Okay. We take the duality of this problem. Of course, the coefficient become 1, 1, right? 1, 1. And 2, 1, the coefficient of the primal problem, 2, 1 becomes the right hand side, 2, 1, right? Okay. And yeah, from 1, 1 becomes 1, 1. Okay. We take same. So this problem, it has optimal solution also at 2, 1. Okay. Yeah. You can try another problem. On the left hand side is primal, and you duality of this problem becomes minimized of this one. Okay. You can take time to look at how we find the duality of the problem. Okay. Now we use one property from the duality. we learned that if one problem is infeasible, the other one becomes unbounded solution, right? So, and remember that for simplex method, we must start from a basic feasible solution. Previously, we solve the problem when we encounter the what is the starting point, infeasible solution starting point, by using two-phase algorithm. But actually, you don't need two-phase algorithm if you use duality, okay? Because we learned that if it's infeasible, the duality of that problem is unbounded solution, okay? So if a starting point is not a feasible solution in primum problem, it is a basic feasible solution in dual problem, always. So we develop new algorithm to solve such problem. What it is? Okay, that one is, yeah. The primum problem is minimized of 20x1 plus 16x2, and we have constraint, okay? And you see that if we change, we rearrange this constraint. We have minus x1 lesser than, we don't care about this right hand side anymore. The right hand side can take negative value because we are dealing with different method now. Okay, and you see that the basic solution is infeasible, right? If we use the simplex method, because the right hand side is negative. Okay, so we construct the tableau from this problem directly, because this is infeasible. We cannot use phase 2 algorithm, simplex algorithm phase 2, because the starting point is infeasible. Okay, so we use the dual simplex method instead to solve the problem, because the starting point is feasible in the dual problem. Okay, so for the dual simplex method, we consider the minimum pivot. We find the minimum C over minus A, and we select the A, the coefficient must be negative. Okay, first select the row as the pivot row such that B is the minimum and negative. Which row? This row, right? The most minimum and negative. Okay, the most negative. And the second step is select the column S as the pivot column such that C over minus A, okay, is minimum. Which column? C over minus A. C, right? C, this C over minus A, and A must be negative. Okay. Yes. Then we have feasible solution. We can further work on that. Okay. I think it's better that you look at the slide and try to understand the algorithm. Okay, but this one, it's it's not simplex, it's dual of the simplex. Okay, the algorithm is here. I show the algorithm here already. Okay, an example is here. Yes. I believe that you can learn it by yourself. Yeah. Fun. And the next one is the linear programming by using Excel. Yes, from Excel, we write the objective function, also, wow, decision variable, and then constraint. Okay. I show you here already what we input in each cell. And then, well, once we start what is it? Solver, what to select from the previous one, you see that? Well, if we set the objective, we set maximum or minimum, maximization or minimization, and then set the row, okay? The decision variable, and add the constraint, okay? When you click add constraint, you have to identify which, yeah. Okay, I think you can follow what I show you in the slide, okay? And in the report, you obtain two reports. The first one is the solution, and the second one is a sensitivity report. I show you here already what is the meaning of allowable increase, allowable decrease, and also shadow price. Okay, can do it by yourself, and then, well, read from the slide. Okay, this is the feasible solution. And the meaning when we change B and C, okay? Gradient. Okay, and also, well, you can solve the problem by using YAOMIP. I put the code here, okay, on the right hand side to solve that one. Also, how to find the sensitivity analysis report using YAOMIP. The code here, okay. For example, for this problem, solve the LP, optimize constraint. Oh, starting from there, initialize YAOMIP clear, and then define declare the decision variable, and then define the objective. Yes. Okay. And sensitivity analysis. Yes, it is done. We finished the linear programming. Of course, you need more time to, well, absorb everything. And repeat the slide again. Try to solve everything, yeah? Including those simplex method, two-phase simplex method, and also duality and dual simplex method. Okay? And try to solve the problem, the linear programming, by using Excel and YAOMIP by yourself. Okay, good. So, yes, you don't, I think you lost our energy now. Okay. Any question from the Zoom? No?
Ajahn.
Yes.
Ajahn, what about the midterm exam?
Midterm exam.
Yes, Ajahn. When will be the midterm exam?
When? I think, well, because of course I think it's maybe we can do it online because some of us are in Taiwan, right? I don't know. They're taking this class, but they are in Taiwan, so we can take it online. But when, I don't know. We have to survey first. Find a way that find the time that all people are available. So it can be during the night time. If we cannot find daytime, we can have exam during nighttime. Is it okay for you? But we have to survey first. Okay.
Okay, copy.
Okay, good. So have a good day. Bye bye.